Hello, I'm Maya Rahman, and I'm going to show you how I made my own ribbon microphone. Let's begin by explaining how ribbon microphones work. In ribbon microphones, a static magnetic field, typically made using two magnets, is held around a strip of aluminum. The aluminum ribbon is extremely thin and clamped in place above and below the magnetic field. When sound is directed at the ribbon, it vibrates through the magnetic field. The vibration induces a small AC voltage across the ribbon, which is the audio signal. This electromagnetic phenomenon is due to Faraday's law of induction, which states that conductive objects that experience a change in magnetic flux will also experience an induced voltage difference across itself. Magnetic flux is magnetic field strength times area, so, with respect to the ribbon, the magnetic field is changing, therefore inducing the signal. Both ends of the ribbon are then connected to one side of a transformer, which, also due to Faraday's law, steps up the voltage based on the transformer's turn ratio. This boosts the small sound signal to mic level, and the secondary side of the transformer is connected directly to the XLR output. Let's start with the motor, the part that holds the ribbon magnet assembly. First, I spec'd out the magnets and the aluminum foil. I chose neodymium magnets that measure 1.5 inches by 1/4 inch and are 1/8 of an inch thick. Neodymium magnets are used in ribbon microphones because they have a strong magnetic field and are pretty robust themselves. I got aluminum foil that's 2.5 micrometers thick, which seems to be a standard thickness for hobbyists. It's light enough to vibrate at all sorts of frequencies, but also not so light that you can't handle it. I began by modeling the motor in Fusion 360, using 3 pieces of acrylic so that the ribbon would be situated in the middle of the magnets and have maximum range between the strongest parts of their magnetic field. Heat-set threaded inserts hold the 3 parts together and provide the threads for the bolts that clamp the ribbon brackets down. I included tabs to help keep the magnets in place while gluing, and hooks in the corners for shock mounting. Satisfied with my design, I laser cut the pieces for the motor and the clamping ribbon brackets out of 3/16 inch clear acrylic. I installed the threaded inserts with a soldering iron and used a plate press technique to get a nice flush finish. I sanded down the magnet cutouts to account for the slight angle of the laser cut, and to keep the acrylic from cracking while installing the magnets. I applied copper tape to the top and bottom of the motor, where the ribbon will be clamped. You need to use the copper tape, as aluminum isn't great for soldering to, and you wouldn't be able to solder to something as delicate as the ribbon anyway. I roughed up one side of each magnet for better adhesion, then glued them into the motor with CA glue. Finally, I soldered signal wires to both strips of copper tape before placing the ribbon to protect it from the heat of the soldering iron. Before I could place the ribbon in the motor, I needed to crimp it to allow for the balance between proper tension and ability to vibrate enough to generate good sound. It took some trial and error, but I ended up 3D printing the crimping gears. The laser cut at too much of an angle to get a nice crimp, and left a line in the middle since the layers of acrylic were difficult to align while gluing. But 3D printing the gears made a clean, straight edge to crimp with. I cut the foil to a 5mm wide strip, then spun it through the 3D printed gears to crimp it. There were a few sacrificial ribbons as I figured out the technique, but eventually I got one that looked nice. Then I used one of the brackets to hold the ribbon on one end, and adjusted the other end until the ribbon was positioned properly. The ribbon needs enough tension that it doesn't sag under its own weight, but still needs to be able to vibrate. I also needed to place the ribbon so it didn't touch the magnets on either side. Once the ribbon was in place, I used a multimeter to verify continuity between either end of the ribbon. Now, where does this all go? In addition to the motor, I designed a housing to hold and protect the delicate ribbon assembly. My first design was angled and boxy, meant to mimic the classic RCA44 ribbon microphone, but I had a hard time generating toolpaths to mill it out nicely, so I tried a different design. The one that I came up with is a more rounded design, with large holes for a grill and insulation to protect the ribbon from debris and large puffs of air. I decided to make it in 3 sections, a 3D printed section in the center to hold the ribbon, and 2 covers milled out of plywood for the front and the back. Once I had the grill cover design figured out, I cut out blanks from large sheets of 3/4 inch plywood using an X-Carve, a large, lower resolution CNC router. Then, I generated toolpaths to cut the blanks into the finished part on a Bantam Tools desktop PCB milling machine. I used a pocket roughing path with a 1/8 inch flat end mill for the inside, then a scallop path with a 1/16 inch ball end mill for a smoother finish. I flipped the part and used pocket and contour paths to rough out the shape. A bore path to mill out the bolt holes and the counter bores, and finally, another scallop path with the ball end mill to smooth it out. I finished the covers by sanding them down. Next came the grill. BigMaster sells metal cloth, and after some Google imaging and caliper estimating, I picked a brass mesh size that I thought would look good. I cut it to shape and hot glued it into place. I layered some scrap fabric behind the metal mesh for a professional look that will protect the ribbon from spit, wind, and debris. I printed the center section on an Ender 3 3D printer using white PLA at 20% infill, and the print only took about 2.5 hours. Then I used the same method as the motor to install the threaded inserts. With the housing done, I used small rubber bands to suspend the motor inside of the center section to protect it from large bumps or movement, and got to wiring. Since the voltage coming out of the ribbon motor is so small, microphones need transformers to step up the voltage to mic level. I used a transformer that has a 1:37 ratio, which is standard for ribbon microphones. When I soldered wires to the motor, I had 2 off the top that came off to the sides, so that the wire doesn't interfere with the ribbon, and to serve as a slight shield to possible EMF noise. I soldered these wires to one of the transformer's primary side wires, and the bottom motor wire to the other. The secondary side of the transformer plus the ground wire got soldered to the XLR connector. I used heat shrink over all of the solder points to prevent short-circuiting and to protect the connections. Finally, to keep the look consistent, I used the same 3/4 inch plywood for the yoke and the base. I made the circular base in 2 halves because I could cut them out quickly with leftover blanks that I had on hand. I milled out the profiles on the desktop mill, then sanded them down and drilled out the holes in the yoke. I used 2 dowels to hold up the yoke because the immediately available dowel options would have been too wobbly, plus having 2 spaced out left room for the mic cable to come down in the center. I used wood glue to adhere it all together, clamping while it dried. Now, I'm sure you're dying to know, does it work? How does it sound? Well, you've been listening to it this whole time. I plugged the mic into a Pro FX 8-channel professional mixer and connected the mixer to my laptop via USB to record this voiceover. I've had to clean up the audio a bit, as there's a mysterious buzz that appeared after my first attempt recording with the microphone, but everything you've heard has been recorded with this mic. Thank you for watching. I hope you've enjoyed this process video as much as I enjoyed undertaking this project, and feel free to ask any questions if you want to know more about my process.